Okay. Yeah, area integral. Yeah.
So what about 1D?
You can use natural coordinates there as well.
Actually,
But
we are telling to use this isoparametric element in 1D also.
in really 1D you can't call it as isoparametric, but you can use natural coordinates, or you can interpolate the you can express the x coordinate or say the basically independent coordinate in terms of natural coordinate and also the field variables. So the approach is similar. No, that is because of Belungundu and Chandru Patla. So because he does that way, so but it is not. I mean, it's the straightforward extension basically. No? So you can use that. So same way, no, you express your shape functions in terms of xi, and then wherever dx is there, so you write ex in terms of xi, and then you dx is equal to some length parameter into d xi, and the integrations then become from -1 to +1. So it's a straightforward no extension. But the main requirement of the isoparametric formulation is to satisfy the inter-element continuity requirement for 2D and 3D problems. So, but you can use, I mean, although 1D problems, natural coordinate formulation as such doesn't have any advantage. If you use a local coordinate system with origin of say local coordinate at first node the way we did, the evaluation of the element level matrices, the governing equations is exactly, I mean, same way the way you would do otherwise using natural coordinates. Those are actually similar, so okay, that's one, so I'll discuss that as well. So then let me I think the other design product design students are here. I know still the class is going. You people didn't attend that class or what? Or today there is no product design class? Pardon? Achha, you are not. Achha, you are not in product design. Okay, so maybe for some more time let me wait, because they had requested 10 minutes. The Thursday class to start at 12:10 rather than at 12, because they have that product design class and that class gets usually a little late. So for them to reach here it takes about 10 minutes. So maybe meantime I'll answer some of the questions I think. So one question was about see when we do the numerical integration. So say for example either you take 1D or 2D. So if we take let us say the example of stiffness matrix. So we are for let us say 2D case it is -1 to +1, and then you have B transpose, in between you will have a constitutive matrix, and then B determinant of J, D high and D eta, and this then we are writing. So the question was about how we actually do that. So say I equal to 1 to n and j equal to 1 to n, and then what we are doing is the whole thing, that is this B transpose C into B into J. This entire quantity is evaluated at xi I eta j, and then you have wi wj. So what it actually means is that suppose you have the element, and let us say that n is equal to 2, your element is a 4 noded element and the properties are such that two integration points are sufficient. So let us say this is xi and this is eta. Two Gauss point means 2 points in the xi direction and 2 points in the eta direction. So one point would be somewhere here, second point would be here, third point would be here, fourth point would be here. So let us say the coordinates are these are let us say this is xi 1 and eta 1, and this is xi 2 eta 1, and then this is xi 1 eta 2, and this point is xi 2 eta 2. So these are the 4 points, no, because it's some double summation, I going from 1 to 2, j going from 1 to 2, so that summation will have 4 terms, and those 4 terms means essentially this whole thing evaluated at I equal to 1, j equal to 1 means actually this point, and then I equal to 2, j equal to 1 means this point, and then again your j equal to 2, I equal to 1, so xi 1 eta 2, and then I equal to 2, j equal to 2, you have xi 2 eta 2. So these are the 4 points. So what it actually means that for defining B, you need to say ultimately B depending on the problem. Suppose it was plane stress, plane strain problem, then your B matrix is like del n1 by del x 0, del n2 by del x, and of that nature. So then you have the terms here, say sorry, this is 0. Say if it was a plane stress, a plane strain problem, so you have del n1 by del y 0, del n2 by del y 0, and so on, and here del n1 by del y, del n1 by del x, and so on. So see, you have to evaluate this. Now what you do is that means to get del n1 by del x, you need or in general say del ni by del x, you need basically the j11 star into del ni by del xi plus j12 star into del ni by del eta. So see, in general these derivatives of the shape functions are in terms of xi and eta. So what it means is, first you take this point, and with the values of xi and eta, xi 1 and eta 1, first you evaluate these derivatives, then you also evaluate your j at that point, because j is also in general function of xi and eta. Of course in specific cases it might be constant, but you evaluate j, then its inverse at xi equal to 1, xi 1 and eta equal to eta 1, and then you find out its inverse, then find out the derivatives of all these shape functions at that point with respect to x, y, and then you define your B matrix, and then you will do this multiplication, multiply by w1 for the first point, and that you will store in a matrix, and then again for the second point you take now xi equal to xi 2, eta equal to eta 1, and then again evaluate the derivatives of all the shape function at this point at xi equal to xi 2 and eta equal to eta 1, and then Jacobian its inverse, then the derivatives with respect to x and y, again define your B matrix at new point, and then do this multiplication, and this multiplication is again added to this existing matrix in that wherever you have already stored this results of point 1 calculation. So then point 2 calculation, similarly 3 and 4. So this is how you basically so that means you have to have a subroutine for the shape functions. So you supply the xi and eta values, it returns you the values of the shape function and its derivatives with respect to xi and eta. You have another subroutine which gives you these, if you send xi, eta and the xy coordinates of the nodes of the element, it gives you Jacobian and its inverse and determinant, and then you have another subroutine sending the values of now the derivatives of the shape function at that particular xi and eta, that gives you B, and then you have a loop which does this multiplication and it stores in a matrix, and when this process is repeated over all the 4 points, so you have the finally your KE. So this is how the integration process, the numerical integration process is done. So is that was your question, that how the xi eta detailed numerical integration, the evaluation of all this process goes on. So this is how it is. Then the another question was about this last class for the 3D element. I had said surface integral, so basically a 2-dimensional area integral. Surfaces are going to be basically areas. Of course, general case they can be curved as well as flat surfaces. Then the third question was about in 3D elements, if you look at we have this J. So another question was about whether we have similar kind of shape requirements for the elements in the physical coordinate space. So when we use, so in case of the way we discuss for 2D, Similar requirements you will have in 3D. So 3D means that is what I think I was mentioning in the last class also, that you have say these elements in the physical coordinate space, and we had the node numbering, if you recall. This is the element in the physical coordinate space, node 1, 2, 3, 4, 5, 6, 7 and 8, and you have the coordinate system. So I had said, say this is x, this is y, and this we had said z, and of course this is mapped to the natural coordinate space. So now when you are doing this mapping, so one of the important thing we discussed was the Jacobian matrix. So if you look at the Jacobian, again if you look at J, which was if you remember, I had defined it as del x by del xi, del y by del xi, and del z by del xi, and so on. So similarly the other two rows. So again maybe I was just answering some queries, okay. So I have not started any new topic, but since there were some questions, so let me. So there was one question about requirements of the shape of 3D elements. So that is the question I was just, the last question I was answering. So the similar to 2D, we had said the included angle should be between ideally should be 90 degrees, and but it can vary from 45 to 135, and also the ratios of the side lengths. Let us say here if I say that this is A, this is B, and this is C. So in case of 2D, we had said ideally again the elements should be square, and of course we allow certain ratios of these side lengths. So similar requirements are there for 3D elements as well. So ideally, if the element is a cuboid, see if the this element in the physical coordinate space is cuboid, that is all these angles are 90 degrees, this angle is 90 degrees, this angle is 90 degrees. So if these all angles are 90 degrees, and A, that is this edge length, this edge length, this edge length, and all of them are same, so that means it is a cuboid. So that is ideal shape of the element in the physical coordinate space, and that gives you well conditioned actually Jacobian matrix. So you will find that if the element is a cuboid, then this you can actually look at the calculations. You will find that then this would come out as A by 2, 0, 0, and I mean if it is just A1 with different A, B and C, so let me first write for that, B by 2 and then 0, 0, C by 2. So this is how your Jacobian will look like. In case the element is a cuboid here, that is all these angles, this is 90 degree, all the included angles are 90 degrees. So that is ideal requirement, because in that case your Jacobian matrix is actually constant, and then when you are looking at the, say if you are using 2 by 2 by 2 integration rule, that will exactly integrate the stiffness matrix, provided the numerical truncation errors are taken care, you use sufficient precision, and there is also, since this matrix would be in general is well conditioned, its determinant is going to be a positive number. So you are mapping the positive volume, positive volume in the natural coordinate space to a corresponding positive volume in the physical coordinate space. So ideally that is what is needed, that these included angles should be 90 degrees. Again, if you look at this ABC, suppose A is let us say 1, and maybe C is 10 to power minus 8. So something like that. Let us say A is 1 and maybe B is somewhere intermediate value, and C is 10 to power minus 8. That means one element edge length is quite large compared to the other element edge length. So then again when we try to invert this J, that is Jacobian matrix, it would be actually nearly singular matrix. It is that is referred to as a ill-conditioned matrix. So we cannot have very large ratios of this A, B and C. So ideally they should all be equal to 1 actually, that is the best, but obviously we cannot have that because the structures would have different dimensions in different directions. So and it is not possible to to decide the number of elements on the basis of smallest dimension, because then the number of elements would go to a very large number. So maybe what is allowed is maximum ratio between any of these dimensions is 10. So you can have one side element edge length, maybe say this is 10, this C can be 1, maybe B is in between, or no, between no, say 10 and 1. So if you have as long as no, this ratio of the edge lengths, that is known as aspect ratio. So in the physical coordinate space, when you discretize the structure and look at the element edge lengths, so the ratios of those edge lengths must be between 1 to 10. 1 is ideal, 10 is what is maximum usually permitted. So that will give you a fairly properly conditioned Jacobian matrix, so that its inverse is properly evaluated. So that is one aspect. The second is now when these angles are not 90 degrees, but they are different from 90 degrees. So then what will happen is, then you see the Jacobian matrix is going to be function of xi and eta. Okay, and when the Jacobian is function of xi and eta, depending on these angles, the dependence of this Jacobian on xi and eta can be quite complex. You know, the powers of xi and eta can go to a higher numbers. So then when you are evaluating this stiffness matrix using numerical integration, I mean similar to this numerical integration in 2D, you have similar thing in 3D what we had discussed in the last class. So that will not be accurate. And to the extent that if these angles are too different from 90 degrees, close to 0 or close to 180, so even you might end up mapping a positive area in the natural coordinate space to a negative area in the physical coordinate space. So for that reason, again similar arguments are that here the included angles also individually, if I look at this face, so then the angle between this edge and this edge, or angle between this edge and this edge, or angle between this edge and this edge, similarly the angle between this edge and this edge, they all should again be similar to what we did for discussed for the 2D, that is should lie between 45 to 135. So that Jacobian is properly conditioned and it is not introducing too much of error if you are using the same order of integration what otherwise you would use if the Jacobian is constant. Although packages sometimes give you some freedom that they will list down what is the although they would have some default setting, but you can actually choose the integration order, what is the number of points you want to use in xi and zeta directions. But usually, I mean, in many cases, this is fixed to what you need for a constant Jacobian matrix. And then if the element is too much distorted, that is going to give error in the stiffness matrix evaluation itself. And also, the Jacobian would become ill conditioned. So even when you are taking its inverse, so that will also introduce errors. So the logic, I mean, again the basically criteria for the shape of the elements are similar to what we have for 2D in terms of aspect ratio and the included angles. For of course 2D, particularly plate bending elements, there are a few more in terms of out of plane distortion, in plane distortion, and the out of plane curvature and the other things. So they also should be within certain limits. So this was another question. So is this clear? So the similar arguments. So actually this is a very good question. I am going to relate this to the next topic what I am going to discuss today. So the next topic I am going to discuss is plate bending element. So before I actually start with plate bending element, let me just summarize that in terms of solid mechanics only. If you look at, although some in between we also took other problems, and similarly you can develop the element level governing equation for, say for example, heat transfer in 1D, 2D and 3D. So far see what we did is, if you look at so far in solid mechanics particularly, we did 1D elements. So in 1D elements what we discussed actually were truss and beam. Beam of course then also had in this I had also discussed 2D frame. Within that 2D in the sense that it can be oriented anywhere in a two-dimensional space. It's really still a 1D element in the as far as the formulation is concerned in the element coordinate system. So we just said 2D frame element. So this is what we have discussed. So you can model the problems where there are only in-plane loads and the cross-sectional dimensions are much smaller compared to the length, either truss. If there are transverse loads, you use beam. If both are transverse and in-plane, I mean axial loads are both of them are there, then you use frame element. And for now the frame can be 3D as well. So then you have you need to consider bending in two planes, so one plane and another plane, maybe you can include twisting in that, axial deformation. So that of course I did not cover, but it's a straightforward extension. One can also talk of 3D frame element similar to 2D, like in the truss we discussed 2D transformation and 3D transformation. So similar way you can have 3D frame element, but then you have to augment the bending in two planes and the torsion, twisting of the beam, and also of course the axial. So you will have two bending in two planes, axial and torsion, these have to be included. So here we did only the axial and bending in one plane. So two more things, bending in another plane and the torsion has to be included. That will get you 3D frame element. So where you have frames which are oriented in space, you would require 3D frame element. So this is what we discussed. So many other problems can be covered under this, and as long as whatever assumption we have made in these, so if they are satisfied, you can actually model those structures using these elements. Then we discussed 2D elements, and in 2D what we discussed was we have plane stress, of course isoparametric formulation in physical coordinate space, isoparametric formulation, 4-noded, 8-noded, so on, various categories under that. So the plane stress, plane strain, axisymmetric. Sometimes some packages they might say axisymmetric under 2D solid kind of a thing, but it's one and the same thing, axisymmetric elements. So this is what we discussed under 2D elements. Then we discussed 3D. So essentially 3D, of course we discussed only one element, and I said that you can degenerate this to tetrahedra. So here we discussed the 8-noded brick element. You can also similarly formulate say 20-noded brick element. So ideally all problems can actually be modeled using 3D element, because in this you are not making any approximation about no variation of the displacement along 3 directions. But now if you think of a situation, for example say a plate like this, so where this dimension and this, they are much larger compared to the thickness. So you can still model this using 3D, apply whatever loads are there, you can solve it, but then to maintain the aspect ratio, so suppose now to capture there is a transverse load, so I want to capture the bending deformation, maybe I have to use 8-noded, maybe 4 elements along the thickness. So you can think of one element edge length is going to be very small, and 10 times of that it would be still a small number. So to then maintain the same aspect ratio, you have to have a large number of elements in the other two directions. So computationally sometimes the use of 3D solid elements or 3-dimensional elements might be more involved, just because we have to maintain certain aspect ratio of the element sides. So because of that sometimes we prefer to use 2D elements, and our 1D elements of course is computationally further more efficient, but then you have to see whether these assumptions are applicable or not. So but now if you look at in terms of loading, so here we consider the in-plane loading, transverse loading, and of course you can have in-plane as well as the axial as well as the bending loads. Here all these problems we only consider actually in-plane loading. So now if we want to do the 2-dimensional problems where 2 dimensions are significant compared to the third one, and but the loads are transverse, so then you have to have one is that you can still use 3D element and model the problem and solve it, but then there is another group of elements which are known as plate bending element. So this is the topic which I am going to start today. So what I am saying here, that you have now a structure, again in that structure 2 dimensions are significant, and third, that is we usually call it as thickness, so that is much smaller, and so much smaller again essentially you have to classify under certain different categories, thick and thin plates. So suppose this is, let me say that is x-axis, I am just choosing a coordinate system, and it has certain thickness, say h is the thickness, and in plane it can be any shape actually, but for the timing let me take a rectangular plate, and this dimension is b, and the loading is now transverse, so means the loading is along the z direction, normal to the significant dimensions, the plane containing significant dimensions of the structure. So now if this is the situation, like I was just giving you this example of top of this table. So because now this dimension is much smaller, I need to have certain number of elements of 3D, and then to maintain the same aspect ratio, I have to use a large number of elements in these two directions. So even though from the solution point of view, that many number of elements may not be required in this direction, but then it because to maintain the aspect ratio we are using large number of elements, it becomes computationally large number of degrees of freedom, so computationally more involved. And particularly if you are actually, although we are discussing here linear problems, but if you are particularly solving nonlinear problems where the solution of simultaneous equation has to be done a number of times, so then there you always try to optimize the total degrees of freedom or the computational time, and there you use the optimal, one is that optimal number of elements and appropriate element type, which is accurate enough but gives you computationally more efficient, it gives you lesser number of degrees of freedom. So that is why then there is a formulation of, so under 2D so far we only discussed plane stress, plane strain, wherein we take only in plane loads, that is loads in these directions, in this direction. Now if there is a transverse load, so such elements are referred to as plate bending, similar to beam element in 1D. Truss is, see this plane stress, plane strain is like truss in 1D, and this plate bending element in 2D is like similar to beam in 1D, that is transverse load. So now again the depending on how much is this thickness compared to the in plane dimensions and what are the materials, you can use, there are different plate theories. So now actually if you look at the modeling of this again, and we are concentrating mainly on the displacement based formulation. Of course when you do advanced courses you will also maybe you can learn about the mixed formulation, where not only the displacements but you also have some stress quantities also as your basically degrees of freedom in the formulation, for example pressure in case of hyperelastic and elastoplastic formulations. So right now I know so far we are only discussing the linear elasticity problems. So here in general if you think of, see the displacement, you will have to have displacement, I mean you have to talk in terms of displacements along x and y, x, y and z directions. So and they in general would be function of all the three coordinates. So similarly v, x, y and z, and w also x, y, z. That is what we did in 3D. But then what we do here, we actually make approximations. So that approximation is along the smaller dimension, that is smaller dimension is actually this dimension. So rather than taking u, v, w unknown in z also, we take some known function in z direction. Now depending on what kind of that function we choose, so you have what is known as classical plate theory, Mendelian plate theory, or first order shear deformation plate theory, higher order plate theories. So there are different theories. What I am going to discuss, of course only one of them, so that is, let me discuss the classical plate theory. So in case of classical plate theory, what is done, that is sometimes referred to as just the classical plate theory or classical Kirchhoff plate theory. So I am actually going to develop the element level governing equation based on this theory, and you can of course always learn the others with the same concept. So here what is assumed is main assumption, like in case of beam I had said Euler-Bernoulli beam, I had said the beam is thin. So similarly here essentially the main assumption is that plate is thin, and meaning of thin is that when you look at this A by H or B by H ratio, whichever is say smaller, if this is greater than, let's say about let me put 30, so this is for isotropic material, and if it is composite this might be 100 or somewhat more in case of composite. And that of course you learn in the advanced courses exactly why this region is. So I am only going to give you a brief idea so that you know that where this is applicable, because here the transverse shear deformation in composites are more significant because their shear modulus is smaller. So the shear deformations are dominant even at higher aspect ratios, A by H ratio. So you need you can use classical theory maybe beyond this, but for isotropic materials you can use, if A by H ratio is something more than 30, you can actually use the classical plate theory. Will usually give you accurate results, at least for static analysis. Of course, if you are extracting higher mode natural frequencies when you do dynamics, this may not be sufficient. Then you have to talk in terms of wavelength to thickness ratio, and that should be fall within these limits. So this is the basically one assumption. So if the plate dimensions are according to this, then you can use the what is known as classical Kirchhoff plate theory. And in this, what you say mainly that normal to the mid surface. Now here you have a middle surface. Like in case of Euler-Bernoulli, we have said that normal to the neutral surface remains normal after deformation. So similarly here also you talk of this normal. So normal to the middle plane, mid plane remains normal after deformation. So that now using this, then we can express the in-plane displacements u and v as a known function of z, that is linear function of z. So what I am going to do before I write here, let me, if I look at this any one section, I just look at the xz plane. Let us say this one. To have a bit more clarity, I am just taking a projection in the, that is front view, that is viewing it from negative y side. So if you look at this is the undeformed configuration of the plate, and when it deforms, so this is undeformed configuration, and this is your x axis, this is your z axis. I am just taking one cut section, and when it deforms, and then this is going to take a shape like this. So say when it deforms, it takes a shape like that. So if I look at any one normal to the middle surface, say if I look at a normal here, some other color let me use. So initially let us say I have this normal. This is normal to the middle surface, and then you have deformed configuration. So this is the deformed middle surface. Now it's a curved surface. This normal would actually now take a shape like this. It remains normal, meaning is that if I draw a tangent here and look at, although I think in the diagram it is not very clear, so this angle would be 90 degrees. So initially this is the normal, that means you have a plate like this, you draw a line here which is perpendicular to the middle surface, apply the load, it deforms. After the deformation, this deformed originally this normal which is deformed here in the original configuration takes this shape, but this line remains normal to this middle surface. That means if I draw a tangent here and look at this angle between these two, it remains 90 degrees. So if it remains 90 degrees, then if W is the displacement along z direction, then this angle would actually be, for of course small deformation, this would be equal to dW by del W, I mean partial derivative, because W in general is a function of xy. So this would be del W by del x. Okay, so once we assume that, then if I have some point here, let us say that I have a point here which is at a distance z from the middle surface, that is from here. This distance is nothing but its z coordinate, that is this distance is z. Now in the deformed configuration, this point has gone here. So it has got displaced along, as you see, along the z direction, and also got displaced along x direction. So this displacement, now I am assuming only that there is a transverse load and the deformation is small, so the middle surface itself does not stretch too much, so we can neglect the deformation of the middle surface. So I can write now this displacement along the x direction is basically going to be this distance, and this distance is going to be z into dw by dx, but it is along negative x direction, so we put here minus z into del w by del x based on this assumption. And this is similar to, if you recall, for the Euler-Bernoulli beam we had written u equal to, of course there I had taken transverse direction as y, so we had written u as minus y into dv by dx. This is a similar concept. So this is in the xz plane. Now if I take the, if I view from the this side, that is from the positive x side, and I can draw another view of this cross section from the other side. So in that case, say this is y and this is z. This is the undeformed configuration. In a similar logic, you can draw the deformed configuration viewed from, see for this we are viewing from this side, and for the other one, if we view some section from negative x, positive x side, this is what you will see, and the plane would be like this in the undeformed configuration, and when it deforms, it would again take a shape like this, and this is the deformed middle surface. Again, if I consider the same normal here, seen from the yz, seen on the yz plane, initially normal, this angle is 90 degrees, and again in the deformed configuration, this remains normal here. That means again if I look at this tangent, and this angle is 90 degrees. If this angle is 90 degrees, that means angle between tangent and this normal, then actually this angle would be again del w by del y. So if I have again the same point here, in the deformed configuration it goes there, and now it is getting displaced along negative y direction, and that would be minus z into del w by del y, assuming that the deformation is small. So this is the assumption. So now what we have done, we reduce our 3-dimensional problem by this to a 2-dimensional problem, because initially we are saying that in general for a 3-dimensional problem, use a unknown function of xyz, v is an unknown function of xyz. By doing this, we are saying that now u is a known function of z, which is linear in this case, and v is also known function of z. In addition, we say that this w is only function of x and y. Of course, because of Poisson's contraction, there would be some variation, but that is negligible. So we assume that w is only function of x and y. So in this process, we are reducing a 3-dimensional problem to a 2-dimensional problem. Now we have one unknown function w, which is a function of x and y. And if we make, here main assumption is that normal to the middle surface remains normal after deformation. So then we have only one unknown variable, that is w, which is function of x and y. Now if we relax this, if your a by h, let's say, is less than 30, then normal may not remain normal, but the angle between tangent to the deformed middle surface and the normal which was drawn in the undeformed surface will be at some non-90 degree angle. So there is a transverse shear deformation. So then you have to consider these rotations independent of del w by del x and del w by del y. So then you introduce actually two more unknowns. Say here you can call this as theta x and this you can call theta y. Then you will have also shear strains in that, transverse shear strains. So that is known as Mendelian plate theory, or first order shear deformation theory. You can take higher order terms here, maybe some z square term into some function, z cube into some function. If you have that, those are referred to as higher order shear deformation theories. So that I am not discussing here, I am just only wanted to discuss that typically for plate bending element how the formulation will proceed. So this is the first step about the approximation of the displacement. Now once you have this, the rest of the steps involved are actually the same, but you will find that there are some difficulties here in terms of ensuring the continuity of w. So you also would look at, similar to if we recall the Euler-Bernoulli beam formulation, since now your u, v, w are the displacement in 3 directions, and if when we discretize a given structure into a number of elements, for this u, v, w to be continuous, that is u, v, w continuous means it will ensure continuous deformed structure, and since u, v, w here are particularly u, v are expressed in terms of del w by del x and del w by del y. So we have to make sure that w as well as del w by del x and del w by del y are continuous across the element. Similar to what we said in case of Euler-Bernoulli, v and dv by dx should be continuous across the element. So now this requires continuity of variable w as well as its first derivative. So this would be a C1 continuous actually finite element formulation, and actually achieving that C1 continuity requirement is not easy for 2D problems, although 1D it was simpler. So we will just discuss what happens after completing few more things in this. So once you have displacement approximation, then you talk of strains. and the strain is similar, no, the same logic. You have epsilon xx, which is del u by del x, and del u by del x is, as you see from this expression in terms of w, this is u, and here what you have is minus z into del 2 w by del x square. Epsilon y is equal to del v by del y, and which would be minus z into del 2 w by del y square. Then if you look at gamma xy, it will be del u by del y plus the same relations we are using. So if you look at del u by del y would give you minus z del 2 w by del x del y, and del v by del x will give you minus z into del 2 w by del x del y. So this will be minus 2z del 2 w del x del y. So these are going to be basically independent components of strains. And of course gamma xz, if you look at, which is del u by del z plus del w by del x, so you will see that this is 0. Gamma yz is, as you see, gamma yz will be equal to again del v by del z plus del w by del y, this will also be 0. So this is what in classical plate theory we are taking transverse restraints to 0. And as far as epsilon zz is concerned, as per this model, because w we have taken only function of x and y, so it actually will be 0, but then when we look at the stress strain relation, we actually use plane stress condition, so we consider some non-zero epsilon zz, but that is not an independent quantity, it can be expressed in terms of epsilon xx and epsilon yy. So I am not writing that. So this is about your strains, and typically what then independent components of strains are only these three. So you can put them in vector form, so you can say epsilon xx, epsilon yy and gamma xy. I need to introduce some of these concepts, because you might have not done this. So I can put this. So I have, one is the w derivatives, which are only which is only function of x, and then z. So whole of this I can write minus z into, say, del 2 w by del x square, del 2 w by del y square, and twice of del 2 w by del x del y. And in the this plate theory, we call this as actually a curvature tensor. So minus z into, sometimes we simply write this as curvature tensor kappa, where kappa is actually, this is known as curvature tensor. And of course here written in the vector form. So this is your strain, independent components of strain written in terms of minus z into kappa. And then if you look at these stresses, now again let me, although you can then generalize this to even isotropic material, orthotropic materials. So let me say that the material we have is linear elastic, and so say the material is a linear elastic isotropic, and let us assume that the plane stress condition. Plane stress here, that means we are going to say that sigma zz is 0. So in plate we are saying that when we have this plate under a transverse load, sigma zz is actually negligible compared to sigma xx, sigma yy and tau xy. Although if there is a distributed transverse load, so on the surface where the load is there, sigma zz would actually be equal to the intensity of load. Of course the other side, if there is no load there, the sigma zz is 0, so in between you will have some non-zero sigma zz, but the magnitude of that is much smaller compared to what you will have sigma xx or what you will have sigma yy. So we actually take this condition of plane stress, that is sigma zz equal to 0. So then the independent components of stresses, sigma xx, sigma yy and tau xy, this we have already used in case of plane stress problem. So E upon 1 minus nu square, and into, then you have constitutive matrix here, 1 nu 0, nu 1 0, 0 0, 1 minus nu by 2, and into the corresponding strains, which are epsilon xx, epsilon yy and gamma xy. And these of course are written here, the way I have written it here. So these are the again non-zero components of stresses. So see, these are the assumption. If you use classical plate theory, means you are taking sigma zz with the this constitutive relation, you are taking tau xz, tau yz, that is transverse shear stresses as well as the transverse normal stress equal to 0, and only non-zero components of stresses you are actually taking these. And then once you have this stress, we also, since the strains are known functions of z, so there is the stress integration through the thickness is defined as moment resultants. So in addition to the stresses, we also talk of here moment resultants. So these are some additional terminologies. So we define moment resultants based on the integration of sigma xx, sigma yy and tau xy, basically the moment generated due to these through the thickness. So what I basically mean here is that if you have some segment of the plate, and if you look at here the same coordinate directions, this is x, this is y and this is z. So for this face the outward normal is, so somewhere here you are going to have your middle surface, outward normally along is x direction. So if I take a small differential area over here, on this face there will be a stress sigma xx, right, and which is of course varying through z, because the strains of functions, the linear functions of z, and therefore stresses will also be linear function of z, so we will have a linear variation. And in addition to on this face you also will have actually tau xy. On this phase you will have tau xy. I am showing that stress on the positive x phase, so you are going to have this as tau xy. Then if you look at this phase, so let me again take positive y phase, and again from the middle surface, if I look at any small area on the positive z side here, you will have stress here sigma yy, that is normal stress, and you will have stress tau xy here, which is your tau, you can say tau yx, which is equal to tau xy. So these are the stresses. So what we do is, now we multiply this stress sigma xx with distance z and integrate it over from bottom to top. We define that as moment resultant mxx. So mxx is defined as integration minus h by 2 to plus h by 2. I am taking the z equal to 0 surface as the mid surface. So then z coordinate would vary from minus h by 2 at bottom to plus h by 2 at top. So you will have z into sigma xx dz. I am only taking the distance along the z direction, not the total area. So it will obviously be the moment per unit here y length. So z into sigma xx dz is actually defined as moment resultant, and obviously you see this is going to be moment about y axis, because here the sigma xx over this area is going to produce a moment like this. That moment is about positive y axis, and this is moment per unit y length, because we are only just multiplying by z into dz, and this is the force per unit area. So it is going to be Newton meter per meter, and that per meter is per meter of length along y. So similarly, if I look at this here, this area, so we define another quantity myy. Myy is again from the sigma yy, integration minus h by 2 to plus h by 2 z into sigma yy into dz. And again if you look at this, he is going to give you moment actually like this, which would be moment about negative x axis, of course. Positive myy means it's a moment about negative x axis on this phase. And then similarly we define mxy. So mxy is again similarly from tau xy minus h by 2 to plus h by 2 z into tau xy dz. And mxy here, if you look at on this phase, due to tau xy, mxy is going to be moment about positive x axis, and on this phase if you look at, that is going to be moment about positive y axis, these two phases. Tau xy will produce, the tau mxy here is going to be moment about negative x axis. That phase if you look at here, mxy or myx would be moment about positive y axis, because on the top side tau y axis in this direction, it would produce a moment about positive y axis. They can be positive or negative depending on the problem, but the positive sign convention for this is that mx is moment about positive y axis, myy is the moment about negative x axis, and this is mxy on the x phase is the moment about negative x, whereas myx on the y phase is the moment about basically positive y-axis. So we call these as moment resultants, and that's the terminology used. So if we do plate, at least we should know this terminology. Again, you can look at this. They can further be expressed in terms of your curvature components. That I'm not going to do here because I will write directly the strain energy wherein I will do these integrations. But sigma xx can be written in terms of epsilon xx, epsilon yy. Similarly this, and then you can do the integration. You can express it in terms of del 2 w by del x square and del 2 w by del y square. These relations. So this is the additional terminology which we use referred to as moment resultants. Then let me now talk of the next quantity which we will use for the element formulation is total potential energy, which will consist of strain energy and the potential of external forces. So this will be, as we did earlier, is going to be integration over volume, and the volume integral we want to split here into integration with respect to x, y and z. Why that? Because we know the quantities variation along z direction, so that integration we want to do explicitly separately. So this we write here the integration with respect to x, y, and the integration through the thickness, which is minus h by 2 to plus h by 2, and then here as usual you write sigma transpose into epsilon, and then you have dz first let me put, and then dx dy. So this is your strain energy. As usual, sigma xx into epsilon xx plus sigma yy into epsilon yy plus tau xy into gamma xy. That is about this strain energy integrated over the entire volume. Then if you look at in terms of external forces and their potential energy, so as I said here at the beginning, there is a transverse force. Let us say that this force is Q Newton per square meter, that is force per unit area. So and that is the force acting along the positive z direction. So Q into dx dy will give you a force over a small area into W the work done, and minus of that will give you the potential of that. So this would be integration only over area, W into Q into dx dy. So Q into dx into dy is the force, because Q is force per unit area, into W work done, negative of that is the potential energy, and the integration only over area, because this is acting only on the xy surface. Although it might be acting say at the top or bottom, but then W is same, we are assuming that W is constant through the thickness, so it really doesn't matter whether load is at the top or load is at the bottom. So same way sometimes the question arises when let us say that you want to model a problem which is using let's say this problem, and you have some distributed force coming from the top and some distributed force coming from the bottom. So let's say a distributed force from the top, a distributed force from the bottom. This side is say Q1, the other side is Q2. So now if the Q1 is equal to Q2, then what would be sigma xx, sigma yy and tau xy? You understand? This is the plate. There is a distributed force from the top side. There is a distributed force from the bottom side in the opposite direction. Let us say that there is a pressure from the top as well as pressure from the bottom, and the two pressures here and the bottom, they are same. So then what would be, as per this theory, what would be sigma xx, sigma yy and tau xy? 0, because Q is 0 effectively. That this Q and the other Q actually cancel each other. So net force in that case is 0. So this Q what we are taking, even if there is a different loads on the top and bottom, it's actually the difference of those two. Of course, because of you have a load from the top, you have load from the bottom, sigma zz, then there would be actually non-zero sigma zz. We equal to the intensity of the load here, but the dominant components of stresses are sigma xx, sigma yy and tau xy, they would actually be 0. So when you do a plate modeling, it is essentially the difference of the transverse load if they are acting on the two top and bottom faces separately. Still for plate bending modeling, it is the difference of those two loads which goes as Q here in the formulation. So this is the distributed force. In addition, because we are actually interested in the finite element, so on the boundaries of that you will have forces, and since you are talking of a plate where there are transverse forces, so expect the reactions from the surrounding elements. One is the transverse reaction, and since your stresses are distributed, so also reaction moments. So you can have the transverse reaction force. That means what I am saying here, that if you have the entire plate, and then this plate is divided into a number of elements like this, and if you are looking at any one of these, so there are elements this side, and so on. So if you are taking any one of this, so if I separate out this element, there are going to be forces from this element onto this element, similarly from this side, and this side. And those forces, one is transverse forces, because external force is itself transverse, so you have to have transverse reaction. And there can also be actually moments, because your stresses are varying through the thickness. So effectively there would be transverse force and moment would be exerted by this element onto this, and that would act on the entire boundary of this element. So boundary integral, say let me just put a boundary integral, and transverse force, let me use say some q n z. So W into q n z is the transverse force. So this is n means outward normal to the boundary, and the force is along the z direction. And you can also have moment, and that moment is now if I follow the same logic, so what I am saying is that when I am separating this element out, so here you have this moment, which is, let us say, outward normal, here is n, so this is m n n moment. As far as the rotation is concerned about this boundary, del w by del x is like del w by del n will be the rotation, which would be actually about this axis, del w by del n. So by the definition of moment resultants and the rotation, they are going to be of opposite sign. So I am putting here m n n into del w by del n. So this is moment and this is the rotation, gives you the work done. And since these are in the opposite direction, work done is negative, so the potential will be positive. So this minus will become plus and into ds. If this is not clear about this sign, I will again, so if I just look at one other face of the plate, say for example this face, wherein say this is x and this is y. As per our definition, mxx on this face, now outward normal is along x direction. So n is your x, so that means mnn is mxx. Mxx is in this direction. But what is your del w by del x? Del w by del x is, if you recall, we said that the normal is initially like this and then rotates like this. So this is your del w by del x, which is the rotation about this axis. So you see here mxx and del w by del x are in the two opposite directions. So that means mnn and del w by del n would be of opposite sign. So the work done is negative, potential is positive, so that is why I am putting a minus sign. So this is going to be the total potential energy expression involving strain energy, potential of distributed externally applied force, and the potential of internal forces exerted onto the particular element from the surrounding elements. So this is all we can have. Of course, we can always add some concentrated forces into this, and then we first want to simplify this. So sigma you can write C into epsilon, so epsilon transpose. So if you look at the further this I, because as far as the z integration through the thickness integration is concerned, we want to separate it out. So this is half the integrations with respect to x and y minus h by 2 to plus h by 2. Sigma can be written as epsilon transpose into C, and epsilon can be written as minus z into kappa. So you will find that one minus z I will have here, minus z into this kappa transpose, then I am going to have C constitutive matrix, and again one minus z, which is actually scalar, and into this kappa vector, which is your curvature tensor, as I said, and then you have dz, dx and dy. So here I have used couple of steps, C equal to sigma into epsilon, sigma equal to C into epsilon, and epsilon is minus z into kappa. So if you substitute that, this is what you will get, and the other two terms of course remain same, that is w q dx dy and minus this integral w q n z minus mn into del w by del n ds. These remain actually same. And now if you look at, see this z is scalar, here I can take it anywhere. C is a 3 by 3 matrix, this kappa is a 3 by 1 vector, its transpose is going to be 1 by 3. So and z is separately scalar, you can take it anywhere. So what you can see that I can minus z, it will become z square, its integration z cube by 3, and when you put the limits minus h by 2 plus h by 2, you will find that it will work out as h cube by 12. So this term I can write simply as h cube by 12, and then I will have here this kappa transpose into C in between, the constitutive matrix, and into this kappa, and now the z integration has gone because we have written it this, and dx dy, and then minus other two terms. Those terms remain same. So this is how we will have finally. What then we actually do is this h cube by 12 into C, we call it as bending stiffness coefficient matrix. So if you look at this term itself, h cube by 12 and into C. So if you see, this remains h cube by 12. C is nothing but E upon 1 minus nu square and 1 nu 0 nu 1 0 0 0 1 minus nu by 2. So this EH cube upon 12 into 1 minus nu square into this whole other thing, usually we denote it as D, and we call it as bending stiffness coefficient matrix. That's the terminology in plate bending. So bending stiffness, to just differentiate from the stiffness of the overall element, we are saying bending stiffness coefficient matrix. So this we call as D, and so finally you can see that your I can be written as half of integration over now the x and y. So you can write that as kappa transpose into this D matrix and into this kappa dx dy and minus the other two terms. This is what you will have. So now if you look at, now next comes is the interpolation. So I'll maybe just talk a little about this, and I think maybe one more lecture is needed on this because this is usually a new topic. I don't know whether you have done earlier any plate bending formulation, particularly about classical plate theory and so on. So probably it's worthwhile to spend one more lecture on this. So now if you look at kappa is, if I rewrite again what we had defined as kappa. So kappa was, if you look at del 2w by del x square, del 2w by del y square, and twice of del 2w by del x del y. So this is our kappa. So if you look at highest order derivative of w present in the integral functional is now second derivative. So whatever approximation we assume, it must be differentiable at least twice. So that is from the differentiability requirement of the approximate solution. The second is, I also mentioned that u and v are expressed in terms of del w by del x, del w by del y. So to make sure that we get a continuous deformed structure, del w by del x, del w by del y as well as w should be continuous across the element. And the first thing to do to achieve that is to have w, del w by del x and del w by del y as elemental degrees of freedom, nodal degrees of freedom. So now if I think of course you can again think of triangular elements, you can think of quadrilateral elements, that is 3-noded triangular element or a 4-noded quadrilateral and so on. So if I talk of, let us say, formulation in the physical coordinate space itself, and let me also take the that's okay. So I'll just conclude. So I think I'll continue in the next class. I stop here, and if you have any doubts and questions, you can ask outside.